morning. So we're going to get started with a new chapter looking at nuclear chemistry. Just pulling up the test grades, making sure we all took our tests. You all are usually really good about that. So let's see. Looks like there are a couple people who did not take the second test and did not email me. So you need to remedy that somehow. Obviously, we're not going to discuss it right this minute. Okay, so let's where did my share button go? All right. So nuclear chemistry, this stuff, when we are working with equations and things like that for nuclear chemistry, they're going to behave differently than, I don't want to say chemical chemistry, but like traditional chemistry where we're dealing with chemical reactions. So natural radioactivity, there are certain elements out there that are naturally just unstable. This is one of them. So we have iodine 131. That's what we would call this. We use the symbol for the element, and then we would put the mass number. And then sometimes you'll see in the lower left-hand corner that atomic number, which is the number of protons. This number here is always the same if it's iodine, right? If it's iodine, it has to have 53 protons. This number can change though. We could pack it with neutrons, making it heavier or lighter, depending on what direction it goes. Now, elements with atomic numbers 20 or higher usually have one or more isotopes that are unstable. So if you go to your periodic chart, usually calcium or larger, all of those guys will have one option of radioactive isotopes. Some of the smaller ones also have radioactive isotopes. So you do have, radioactive carbon and stuff like that. It's just not quite as prominent. Why is it 20 or greater? That's because the atoms start to get bigger and their nuclei start to get clunky, and they want to break apart into something that's more stable. So an unstable nucleus is radioactive, or if an unstable nucleus is radioactive, it will emit or give off energy that we call radiation to become more stable. And there's a couple different ways that it can radiate energy. It can take the form of an alpha particle, a beta particle, and the alpha has this little italicized A thing. A beta particle, which has this sort of B shape, a positron, which is like the beta particle, but it has a little plus symbol, or it can release it as pure energy, which is a gamma ray, which is this sort of funky Y shape. We will go over each of these and what they are. An isotope of an element that emits radiation is called a radioisotope. So if we had isotope as our umbrella term, we could break it up into a radioisotope, which is radioactive, or a stable isotope, which is stable. When radiation is emitted, so when we release one of these alpha, beta, gamma, whatever, there may undergo a change in the number of protons, and it may convert an atom into a different atom, which is a little bit strange from what we've talked about thus far, right? In chemical reactions, if you start with 2 aluminums, you better end with 2 aluminums. That is not going to be the case in nuclear chemistry. You could start with an aluminum and you could end with a nitrogen. So here is our way, one way of writing an isotope. Here are some of the other ways too. Iodine 131 or iodine 131 here, I with just the I. I kind of prefer these because they require less numbers to write. Here, when you're writing this with iodine and 131, 53, I mean, the 53 and the I are redundant. If I go to my periodic chart and I see I, it's always going to be 53 as the atomic number. So let's see. So stable and radioactive isotopes for some elements. You do not need to have these memorized. Okay. There are lots of isotopes out there, but just some things that we look at. Some stable isotopes. So magnesium 24, which is 12 protons and 12 neutrons, is stable. That means it's not going to decay. You can write it like this, or we can write it as magnesium 24. Now there is a radioactive version of magnesium, magnesium 23, which has one less neutron. For whatever reason, that is particularly unstable in the nucleus. So this thing will degrade. Also, magnesium 27 is another radioactive isotope. Okay, different ways we can write it. What is changing here? Well, the magnesium is still staying magnesium in each of these because it has 12 protons, but the number of neutrons is shifting. Here are some isotopes for iodine. So iodine 127, for whatever reason, that configuration is stable, but iodine 125 and iodine 131 is unstable. Uranium, there are no stable elements of uranium. So if somebody gives you a hunk of uranium and says, no, 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 this is the stable isotope of uranium, don't believe them and put it next to your bed, okay? You definitely don't want uranium decaying anywhere near your lovely body. So 235, 238. So let's go through some of the types of radiation that we have. The first one, which is kind of like the clunkiest radiation, is known as an alpha particle. An alpha particle is 2 protons and 2 neutrons, and it has an overall 2+ charge that a lot of times we just omit the positive charge. There's no electrons in this alpha particle. It looks sort of like this. Sometimes you'll see it written as just a helium nucleus because that's what it is, right? 2 protons is helium. So helium, symbol helium, will have a 4 in the upper left-hand corner and a 2 in the lower right-hand corner. Again, this is a really clunky particle, so this isn't too invasive like for biological systems. So if alpha particles are getting shot at you, usually you can deflect them with like a lab coat or something like that. A little bit more high energy, a beta particle. So a beta particle is a high energy electron with a charge of -1. And it's formed when a neutron is changed to a proton. This is totally different than what we were dealing with in chemical reactions, right? In chemical reactions, we kept protons, protons, and neutrons, neutrons, and this and that. Well, this is all going to sort of shift here. So if I take a neutron and I shift it into a proton, and look at the symbol for a proton. Do you see how they have it as hydrogen with a 1 and a 1? Remember, the top is the mass, the bottom is the atomic number. So a proton is going to be, it's going to have 1 proton and it's going to have atomic mass of 1, meaning it doesn't have any neutrons. It's just a proton. So when a neutron turns into a proton, well, how does it do that? A neutron has a neutral charge, a proton has a positive charge. So in order for a neutron to convert to a proton, it has to release a negative charge, right? It has to give up a negative charge to become a positive. And so it gives off this beta particle, which is a higher energy electron. Again, let's just look at what some of these particles, their symbols are. So an electron is going to have an E. In the lower left-hand corner, it's going to have a -1. The -1 is because it's the opposite of a proton, right? This lower number usually tells us protons. And protons have a positive charge. So if you have a -1, it's saying you have one of the opposite of a proton, which is an electron. But it's also telling us that we have in the upper left-hand corner, our atomic mass is 0. So it's something with a minus charge that has a 0 mass. That's an electron. An electron has a negative charge with no mass. A neutron over here. It's got this little N symbol. The lower left-hand corner tells us how many protons. Well, how many protons does it have? 0. what's its atomic mass? 1. So it weighs something, but it's not attributed to a proton. So it needs to be the neutron. And then we've got our helium over here, which is 1 proton, and the entire mass is just taken up by that proton. So getting comfortable with writing symbols like this. A positron is sort of the opposite of a beta particle. It's even the same symbol, but it has a plus on it. So this is your first example of and encounter with antimatter. So it's a positive electron, and it's produced when a proton wants to turn into a neutron or shifts into a neutron. If you're a proton, so we've got this over here, and we want to become a neutron, we have to get rid of our positive charge. How do we get rid of our positive charge? It happens by emitting this positron thing. So let's look at the symbol for that. It's also got the E symbol, so it's like an electron, but the shift happens down here. It says we have a +1, so we do have a +1 charge, but we don't have any mass. So we're just sort of a positive charge floating around. So it's kind of a new concept for you guys. One thing to note, and we will kind of go over it, but the values on the top and the values on the bottom when you're writing a nuclear equation need to equal each other, okay? So if you look here, there's a 1 on the top. That means that this plus this also needs to equal 1. Okay, so whatever's on the left needs to equal what's on the right as far as your atomic mass is concerned. Same thing with your atomic numbers. So the values on the bottom need to equal each other. So on the starting side, I have a 0. On the ending side, I have a 1 and a -1. A 1 plus a -1 also gives me a 0. Those equal each other. That's how you're going to balance nuclear equations, okay? It's not going to have anything to do with the number of atoms. It has to do with balancing atomic mass and atomic number. So we will practice that a bunch, but I just want you to sort of see how that's happening here, right? When we've got a proton and it turns into a neutron, well, that's the same mass. So our positron doesn't need to have any mass to balance that out. Over here, our proton has a charge of +1, our neutron has a neutral charge, so something has to balance that out with a +1 charge. That's where the positron is getting it. The last type of radiation, which is very, very high energy radiation, is gamma rays. This is what comes off of very intense decay, like plutonium, uranium, things that are in atomic bombs, things that are in nuclear power plants, stuff that's coming off of the sun, okay, very, very strong radiation. Gamma rays have a symbol of this little Y here, and it's a 0 mass, 0 mass and 0 charge. So no mass, no charge. What's happening here is we have a beta particle and a positron coming together to produce a bunch of matter. So matter and antimatter are coming together to produce pure energy. There's no mass when you have matter and antimatter. They counteract each other. Sorry, my daughter snuck in. Oh, that sound. She's got some lungs on her.
Where does that 2 come from?
The 2, because you get 2 of these. Yeah, good question, Cecilia. You get 2 of the gamma rays. So yes, one, sorry, she's driving me crazy. Okay, one beta and one positron will produce 2 gamma rays. That's how we balance it out.
So is there like an inferred 1 in front of each of those?
Of these things, yeah.
Okay, is that going to be the same for
all these? Yeah, we can assume that there's one of these, one of these, one of these. If for some reason you had 2 like neutrons, it would have a 2 in front of it. Okay, and I actually do think later on we see that where like something will produce 2 neutrons. Okay. So yeah, do keep looking out for coefficients. All right, so here's a good chart that has all the symbols on it. So you may want to review or have this handy. It's got the different symbols, including how you want to write them when you're writing equations. It also has the mass numbers and it has the associated charges. So, you know, for instance, a proton is a hydrogen atom without an electron. It's 1 and 1. It has a mass number of 1 and it has a charge of +1. That's what we would define a proton as. So give the name and symbol for the following types of radiation. You don't really need to go through all this in such detail, but alpha radiation, so that's going to be our alpha particle, right? The helium with the 4 and the 2. Memorize it, conceptually understand it, have it accessible, whatever works for you. Radiation with a mass of 0 and an atomic number of +1. So if we have a mass of 0, that will go on the top. An atomic number of +1 means we have a positive charge with no mass. That's going to be a positron. Radiation that represents high energy, radiation released from the nucleus, that's going to be a gamma ray. So biological effects of radiation. So when radiation strikes a molecule, it may knock away some electrons, forming an unstable ion. It can also interact with water molecules, removing electrons and producing this thing right here, H2O+, which can cause undesirable chemical reactions. What is our body made of? Well, our body is made up of a lot of water molecules. So, you know, if you start to spend too much time near radiation, it can have both of these effects simultaneously. 1, affecting the water in your body, 2, affecting the actual cells in your body, which can lead to overgrowth of cells, cancer cells, all sorts of different things. Cell division, increase in cell division. So how do we protect ourselves from different types of radiation? Alpha particles, again, those are the helium atoms. Those are the clunkiest. Usually paper and clothing can stop alpha particles. Okay, so unless you're like digesting the alpha particles, you're eating them in some sort of liquid, you can protect yourself with a heavy shirt. A lab coat and or gloves can help with beta particles. As far as gamma rays, you're going to need like a lead shield or some sort of concrete. All right, so if there was a nuclear holocaust, you'd have to get into a bunker. You wouldn't put a lab coat on because that is such high energy, it can pass like right through your body. Other ways to protect yourself against radiation. Big one, limit the amount of time you spend near a radioactive source. Okay. Increase the distance from the source. So if there is a nuclear bomb that went off, or if there was a meltdown at a nuclear power plant, you want to create distance between you and that radioactive source. So that's sort of like common sense, right? If you work in an environment where radioactive material is present, you try and keep your time to that radioactive area or material limited. So traveling in the air, okay, we don't really need to get into all this. What type of radiation will block each of the following? So lead and shield would block alpha, and it would also block beta. Paper and clothing could block just alpha. Oh, lead shielding would also block gamma. It can block all of them. Okay, so nuclear reactions. This is kind of fun. I think these are kind of fun to do, but when you have a really large radioactive nucleus, like right here, I've got this uranium nucleus, specifically uranium-238. If I told you this nucleus undergoes alpha decay, that means that it's going to release an alpha particle, and then it's going to have a remaining atom. And that remaining atom is going to be short 2 protons and 2 neutrons, right? Because at the end of the day, it's not about preserving the atom type on each side of the nucleus. It's about preserving the number of protons and neutrons in atomic mass. So we need to have the tiny subatomic particles here need to equal each other on both sides. So in a balanced nuclear equation, particles are emitted from the nucleus. This will shift the type of atoms that you have. The mass number and atomic number may change, but the sum of the mass numbers and the sum of the atomic numbers will need to be equal for reactants and also for products. So if I've got CF251 here, it has a mass number of 251. It has an atomic number of 98. That means that whatever's produced on the other side, the two top numbers will also need to equal 251. And the two bottom numbers will also need to equal 98. And in that case, that is correct. So if this is undergoing alpha decay, right, we've got 247 and 4, which gives us the 251. We've got 96 and 2, which gives us the 98. Now, because you know this value, because you know your starting information is 251 and you know your ending information is 251, right? I could say, hey, it undergoes alpha decay. What is this particle? And you could actually solve for this particle pretty easily, because if you know it needs to total 251 and 4 of it is coming from here, well, the remaining 247 has to get attached here. And you can kind of work backwards through subtraction to get maybe the mystery element that's produced. So first type of decay, alpha particle decay, a new nucleus will form. That new nucleus will have a mass number that is decreased by 4 and an atomic number that is decreased by 2. That's sort of consistently how it works. So if I've got uranium-238, it undergoes alpha decay. You know, it's important to see what the problem is saying. In this case, it's specifically saying alpha decay. So right away, you can write your alpha particle. And you have, let's see, so our nucleus, well, we were at 238. I need to subtract out 4, so that'll give me 234. I was at 92. I need to subtract 2 to give me the 90. I just look at the identity of what 90 is, right? So 90 on the periodic chart is thorium. So I knew the new nucleus will be a thorium atom. So when writing one of these equations, write the incomplete nuclear equation first, determine the missing mass number, determine the missing atomic number, and then figure out what the symbol is to complete it. So let's do this one. Americium-241 undergoes alpha decay. I want you to tell me what the new mystery nucleus is that's formed, or new mystery atom that's formed. This one here maybe is a little bit clearer. So you've got, this is what you're starting with. You know one of the ending pieces because it specifically says it's undergoing alpha decay. So I'll give y'all 2 minutes for that. Okay, so We only have one starting thing. There will be times where you have two starting materials, but here we just have one. Okay, the top value is 241. So that means that on the opposite side of the arrow, I also have to have a total value of 241. 95 on the bottom, 95 on the top. So we just go ahead and subtract 241 minus the 4 that's coming from the alpha particle will give us 237. So our mystery nucleus has an atomic mass of 237. The atomic number, well, we had 95 and we've got to strip 2 away that's being eaten up or occupied by the helium, right? So my new mystery atom has an atomic number of 93. So 237 and 93. Well, you go to your periodic chart and you look up what is 93. And Neptunium is our 93. So our missing component in this would be Neptunium 237. And it should end looking like this. Here's our 241. This and this add up to the 241. Here's our 95 and the 93 and the 2 add up to the 95. Any questions on that, on how to balance that? It's a little bit different. I think these are kind of fun to do. I don't know why, I kind of like them. I want to talk about what is going on with the lab. No, you don't need to see that. Let's see. All right. So traditionally the labs are in your lab manual, right? Well, part of the nuclear chemistry lab, part of it is in your lab manual, but part of it is sitting right here, okay? So you're gonna need to click on this. This is the second part, and it will give you a lab to fill out, all right? And you can write on it in your computer and then resubmit it to me, or if you want to, you can print it out. But this is going to give you a bunch of practice on all of this stuff. So actually, let's look at a couple for here. So I want you to do the first two, and then you won't have to do them a little bit later. So polonium-208 and thorium-232. Both of these are undergoing alpha decay. So I want you to write an equation for both of these that represent alpha decay. It only gives you the starting. So I'll give you a little hint. Here's an arrow. You need to move to the other side. Okay? If it's alpha decay, you know what one of the particles is for sure. So I'll give you all 4 minutes to work on that, or 3 minutes. It's not that hard. If you plow through those, you're more than welcome to get the other 2 done so that you can just fill it in later. Okay, so if this is undergoing alpha decay, you can like right off the bat write an alpha particle. So an alpha particle 4 to He. 4 to He. I mean, you can just like do that for all of them. So I've got 208 here. That means that the total on this side needs to be 208 as well. So 208 minus the 4 is going to give me 204 for my top value on this mystery element. I've got 84 on the bottom. That means 84 on the bottom here. 84 minus the 2 would give me 82. And then I look up on my periodic chart. Where are you? 82. 82 is lead. Okay, so our mystery element for that first one is lead 204. Next one, I've got 232 on the top. We're going to subtract 4 to give us 228. Right? Okay. And then 90, 2 of them are being occupied by the helium. So that's going to give me 88. And then I just need to look up what the material is for 88. Where are you? 86. Radon. Or radium, sorry, radium. Ra. You'll feel okay with that. It's not too difficult. It's a different way of balancing, but it's not too hard if you know what an alpha particle is. And it sort of becomes like a repetitive thing. So you guys good with alpha decay? Cool. Let's move on to beta decay because we've got other particles to talk about. So if we undergo beta decay, it's a little bit different here. In beta decay, so the beta particle gets shot off, which is an electron. But remember, what did we say about beta decay? Beta decay is when we have a neutron that pretty much turns into a proton. So when you undergo beta decay, a neutron in the nucleus breaks down to form a proton and a beta particle, increasing the atomic number by 1. So consistently, your atomic number, or the number on the bottom, will increase by 1, but your mass will stay the same, right? Because you're not like getting rid of one of these big particles, you're just shifting one thing from a neutron to a proton. So carbon-14, when it undergoes beta decay, the atomic number will stay the same, so it's still 14. The number of protons will increase, or the atomic number will increase by a factor of 1. So from 6 to 7. So it went from carbon-14 to now we have nitrogen-14. The same thing falls true if you don't want to remember that, oh, it increases by 1. Well, if you know what a beta particle is, just make sure that the things on the top add up and the things on the bottom add up. So I've got 14 here. If I've got 14 here, the two tops need to be 14. Okay, so this is 14 and this is 0 for a total of 14. The bottom here is 6. Over here, it's turned to 7, minus 1, right? Or if this is a minus 1, this needs to be a 7 to counteract the minus 1 to get me back to 6. So go ahead and do it for potassium 42. Okay, let's say this thing is undergoing beta decay. There is our beta particle. I want you to tell me what the mystery nucleus is. Okay, so either knowing that one of these, but this number is going to go up by 1. This will stay the same, or you can use addition and subtraction, right? This is 42, so this also has to be 42. This is 19, so this needs to be 19. So that bottom thing needs to be 20, right? The top thing will stay 42, and you look it up, and it should be calcium 42. Did I do that right? Yeah, okay. Yes, calcium 42. So let's do, just to really stick it in that brain of yours, let's do a couple beta decays. We'll do 2 of them. So here are a series of things that are undergoing beta decay. I just want you to do A and B. Again, if you are, I'll give you 2 minutes. If you're super fast, you can get through all of them. Okay, so traditionally, a lot of times you'll see the particle that's getting released put as the second component. I kind of like to put it as the first. So you may see me go like this, 0. If it's beta, it's a -1 and it's an E. But if you see that as a secondary thing, or you write it as a secondary thing, that's okay as well. So what is our mystery nucleus that we've produced? Well, the number on the top will stay the same because this is a 0. The number on the bottom needs to increase by 1 because here is a -1. So instead of 11, it needs to be 12. And how do I not have this memorized? What's 12? Magnesium. So magnesium 25. Next one, we had oxygen 20. The 20 is going to stay the same. 8 needs to go to 9. So instead of oxygen, it is now fluorine. Fluorine 20. And you just sort of continue the pattern on. Good with that? Good with beta decay? Cool. All right. Let's see what else we got in here. Yeah, we already practiced that. We're good. Okay, so positron emission. So remember, a positron is the opposite of a beta particle. It's when a proton is converted into a neutron. So in that case, the mass number of the nucleus stays the same, but the atomic number should decrease by 1 because a proton is changing to a neutron. So here I've got manganese 49. The 49 should stay the same on my new mystery nucleus. But because we're giving off a positron, which is a +1, one of these protons has been stolen, right, or converted. So the 25 will drop down to a 24. So it does the opposite of what beta does. Beta, you increase the atomic number, or you increase the number of protons by 1. Positron emission, you decrease the number of protons by 1, or the atomic number. I don't know if the lab has specific positron. Let's see. We've got beta decay, alpha, beta. These are more complicated. Yeah, doesn't look like they specifically have one. I'll give you one. So let's say cobalt 60 undergoes positron decay. Write an equation. Sorry, that looks like carbon 60. Let's actually call it what it is, cobalt, CO. Sorry. Okay, so I gave you cobalt 60. I didn't give you the atomic number, so you just need to have a periodic chart with you. So 60 cobalt, if it's cobalt, it should have an atomic number of 27. If it undergoes positron decay, that means that we have a mass of 0, a charge of 1, and it has the little electron symbol. This is the positron. What is our new nucleus that we form? Well, the top number will stay the same, 60. The bottom number, 27, it has to drop down 1. So it'll become 26, and that's iron. So iron 60. All right. The last type of radiation that we get is gamma radiation. Now remember, gamma radiation doesn't have any mass and it doesn't have any charge. So it doesn't actually change what the original atom or nucleus is. It just strips away some of the energy. You kind of think of the nucleus as having like energy to it that it needs to get rid of, and it releases it through gamma radiation. Sometimes the energy that's in the nucleus will be indicated with like a little M symbol like this, following the mass number. So it would be 99 with a little M, and then TC, and then it undergoes gamma radiation. So here's the gamma radiation, but the number stays the same and the identity stays the same. So it's, you don't get a new nucleus, you just get a more stable nucleus. That one is probably the easiest of them to balance. Okay, so here's kind of a summary of what happens if you have a alpha emitter, something that's going to give up an alpha particle. You'll have an alpha particle and a new element. That's mass number is down by 4 and atomic number is down by 2. That's how you read it. Again, you don't really have to have all these memorized. If you just know what each of the decay particles are, and you know that the top values need to equal and the bottom values need to equal. So how do these radioactive isotopes form, right? Like if everything's trying to decay to something stable, you'd kind of think, well, shouldn't everything eventually decay to something stable and we'd never have anything radioactive again? Well, radioactive isotopes get produced when you have what is originally a stable nucleus and it gets bombarded. Sometimes it's called transmutation, where you have a particle that bumps into a stable nucleus. So here I've got a bombarding particle. In this case, it's an alpha particle, and it gets smacked into this stable boron nucleus. Those two things kind of smoosh together, and you get a new radioactive nucleus. And in this case, these two things hit each other. We produce a radioactive nucleus, and it also emits a neutron. So this process, again, can be called considered transmutation, or sometimes you'll hear it called bombarding. So when writing an equation for a bombardment, let's look at this one. It says, write the balanced nuclear equation for the bombardment of nickel 58 by a proton, which produces a radioactive isotope and an alpha particle. So let's say that this isn't currently here. So we're given just this top part. So what is getting bombarded or what's getting smushed together? Well, you've got a nickel 58 and you've got a proton. So those are your two starting things, which produces, so that's sort of the thing that cuts off your starting and your ending. You have some sort of mystery radioactive isotope and an alpha particle. You know for sure three of those things, right? You know the nickel 58, you know the proton, and you know what an alpha particle is. So you should be able to find the radioactive isotope just like you found the other ones. So when writing it out, you're going to want to write out your proton. So here's our proton, which is also just a hydrogen nuclei. Here is our nickel 58. All right, nickel 58, and the 28 is coming from its atomic number. If it's nickel, it's always got a 28. It said that it produced an alpha particle, so you know that one of your products is going to be the alpha particle. Boop, 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 boop. And then the last step is to figure out what this mystery nucleus is. The same thing applies when you're doing bombardment. The top values need to equal each other. The bottom values need to equal each other. The only difference here is you have two starting things. So instead of just having one for 58, you have to take the 58 and you need to add it to the one. So the total is 59 here. Total here would be 59. 28 and 1 gives us a total of 29 here. So we need to have 29 there. All right, so 59 minus the 4 would give us 55 for our top. 29 minus the 2 coming from the alpha particle would give us 27. And we just look that up and it's cobalt 55. So same rules apply. Add the top things, make sure they equal each other on both sides. Add the bottom things and make sure they equal each other on both sides. Chances are you won't be given it or not chances, but there will be times when you're not given it like this, you're given it as a word problem. So just read it out. What are you starting with? What are you ending with? So here's one. I want you to solve for the mystery. Here we've got TC98 is getting bombarded by a neutron. You get an alpha particle and some sort of new nucleus. So you calculate out what the new nucleus is. Okay, so we've got a total top value on the starting side of 99. 4 of them are getting consumed with the helium. So 99 minus 4 would give us a 95 for the top value. 43, a neutron doesn't have any atomic number to it. So 43 for both sides. 43, 42, 41. And then we look up 41, NB. Yes. Okay. So let's do a couple of those from the homework, or rather the lab. Why not? Let's just get them done. Let's do all 3. Okay. So all of these are some sort of bombardment, meaning that we have 2 starting things. Sometimes you have to solve for the end. Sometimes you have to solve for what is getting bombarded, or the starting component. So I want you to find the missing question mark for each of these. Okay, so this first one is a beryllium atom and it's being bombarded by a neutron. And there's just one product. So top values need to equal each other. So 9 and 1 is 10 for the top. 4 and 0 is 4. So we're actually just a heavier version of beryllium. Next one, I have sulfur and it bombarded with something to produce phosphorus. So we've got to figure out what that something is. Well, 32 and 32, that means that whatever this mystery thing is it has a 0 atomic mass. As far as the charge is concerned, this is 16 over here. This is 15 over here. Those have to equal each other. So this has to be a -1. Right? 16 plus a -1 would give me the 15. So what is the identity of this? Give it an E. It is a beta particle. All right, something big and clunky is smashed by a neutron and we get these two things. So we've got to figure out what that is. Well, 24 and 4 gives me 28. This also has to be 28, but one of them is being consumed by a neutron. So our mystery element has a value of 27 on the top. Sorry, I'm writing it below. 11 and 2 gives us 13. And this is 0, so the bottom thing also has to be 13. So what is the identity of our 13? It is aluminum. So aluminum 27 is hit by a neutron to give us these two things. You guys seeing how that works?
For B, when I'm looking at, maybe I wrote my notes wrong, but I had the positron emission as what would be losing, or
so if we just go off of the addition and subtraction of it, if I made it a positron, okay, let's say that this was plus instead, that would be 16 plus 1 would be a total of 17. What's the total on this side?
15.
15.
Okay. But then why is it on the positron that, like, for example, we had like cobalt 27 turned into iron 26, but still was a +1.
Well, 27, that was for that's because we're doing bombardment, not emission.
Gotcha. Okay.
Yeah, so it is important, like what side the particle is on, totally. Yeah. So if you're doing, you can kind of consistently, if it's positron emission, know what's going to happen, but this is a totally different area where we're bombarding them.
Okay.
So let's see where we at. And so we're going to talk about this radioactive measurement. So this dude here has what's known as a Geiger counter, and it has a reader in it that clicks every time it's measuring a certain amount of radiation. My audio has something going on. If it's off, maybe just pause for today. All right, we'll just call it for today if there's some issues with that. So we will get back to this next time. You should be able to do a good majority of your homework with your audio is weird. Okay. So you should be able to do a good amount of the labs and homework with what we've done thus far, but we've got a little bit left to go over. So I will see you all on Thursday. Have a good rest of your day. Bye, everybody. If you have a question, stay around.